So thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Laura Cui, who will tell us about unitary designs in nearly optimal depth. So Laura is a third-year graduate student in physics at Caltech. Her supervisor is John Freskill and Fernando Randao. She is broadly interested in the intersection of quantum information and many-body physics, particularly problems related to the complexity of quantum dynamics. So Laura, the floor is yours.
Okay, thank you so much for the introduction and also for inviting me to be here today. So I want to mention that this is joint work with my collaborators, in particular with Thomas Schuster, who is co-first author on this work, as well as with Fernando, my advisor, and with Xingyuan or Robert Huang. Okay. And we also have our archive number here in case you would like to look at the paper. Okay, so just to get started, the broad motivation of this line of work is to really understand random states and unitary processes. And these come up in a lot of ways in quantum information science. So for example, from the many body physics perspective, we're often interested in using random states and unitaries to model universality in very chaotic, generic physical dynamics. But then from a more computational perspective, we're also often interested in randomness as a sort of computational primitive or as a way of understanding randomized algorithms and so on. And these have a lot of applications. So in particular for near-term quantum computing, people are often interested in benchmarking their devices and characterizing the kinds of noise they have in their system. So for example, there are many recent works such as this one, which use random unitaries to characterize the outputs of the circuits. And then more broadly, we might also be interested in the complexity of randomized algorithms, which are particularly natural when generalizing to quantum algorithms as well. And we might be interested in understanding the complexity of different kinds of algorithms and whether there's hope for obtaining quantum advantage for certain types of tasks. Okay? So given all that, one very key question that you might ask is, what is the circuit depth that's actually necessary to emulate a random unitary for all of these tasks, right? So in what circumstances can we actually construct circuits that reproduce the outputs of random unitaries? So one model that's been very commonly studied are these brickwork random circuits. And so here we have just like a 1D architecture where we have n qubits placed on a line. We just have these 2-qubit nearest neighbor gates. And each of these gates is chosen independently and uniformly at random from all unitary transformations on 2 qubits. Okay, and then we also have, let's say, a fixed number of layers, say T layers of these gates. And you might expect that this converges to something that looks fairly random on the entire system. And in fact, this is the case. You can show that these kinds of random local circuits with 2-qubit gates or 2-qubit gates more generally do in fact converge to random unitaries in the sense that the moments of the distribution converges to that of a uniformly random unitary. So it's shown in this very early work from Brandau, Harrow, Hordecki, that the measurements on the output of this kind of circuit will look random after some depth, which scales with the size of the system. And there are some more recent works that actually suggest that using some coarse graining arguments, we can improve the circuit depth of a similar sort of uniform circuit architecture where we have gates that are chosen independently at random. And we can actually obtain a random looking unitary circuit using only O of log n layers in this circuit. Okay. All right, so this is very exciting, but it still leaves the open question of whether or not this is really a optimal circuit depth. And in particular, we might be sort of interested in this from the perspective of information dynamics. So we can ask, is there a sense in which uniform random circuits where we choose all of the gates independently in some sense, are these kinds of uniformly random circuit architectures optimal at scrambling the information in a system, subject to restrictions like having a local gate set and so on? And the answer surprisingly turns out to be no, actually. And this might not be obvious until I describe our construction. But it turns out that we can actually get exponentially lower depth using a structured circuit to scramble a subsystem, in this case, using some number of ancillas as well. Okay, so before I get into details, let me just make this a little bit more precise. So whenever I talk about random states and unitaries, I'm going to be referencing something called the Haar measure. This is a well-defined probability measure. It's the unique invariant measure on U2 to the n under some unitary transformation, so either left or right transformation. And this just makes it sort of a uniformly random equal measure or equal probability measure over the unitary group. And similarly, we can also say how random states are ones that are sampled from a distribution, which is also invariant under some unitary transformation. So any two given states in the Hilbert space are equally likely to be sampled. Okay, so now if we look at our Hilbert space and we want to sample some uniformly random state from this Hilbert space, we can ask, what is the complexity of doing this? So how complex are some of these typical states? So in general, it requires exponentially many parameters to simulate this kind of typical Haar random state or to construct it. And this is true even if we allow for some approximate representation of this truly Haar random state. Okay. So that's a bit unfortunate for us because it means that if we really want a state that is uniformly random somehow over the Hilbert space, it's actually very hard to do so even on a quantum computer. However, we might ask if there's a way to somehow get a lot of the properties of these Haar random states and unitaries without reconstructing like a fully uniformly random state. It turns out there is a way to do this by looking at the statistical moments of the Haar distribution. So the idea here is that we can expand functions of a distribution in terms of the moments. So if we take the expectation value of some function, and this function is a smooth function, then we can write it in terms of some moments. And for the moments of a matrix value distribution, such as the Haar measure, one way to do this is to use these twirling operators, where we take in some linear operator x, and we ask about its moment relative to the Haar measure by taking k copies of some random unitary and conjugating x by it. So this is also called a twirling operator. And then similarly, for the moments of the Haar distribution over states, we can take a uniformly random state over the Haar distribution by considering just k tensor copies of it and averaging over the unitary group. Okay, so then we can think about what kinds of ensembles reproduce the lower order moments of the Haar distribution. So we would call these unitary and state designs. So state designs should approximately reproduce the lower order moments of this uniform distribution over state vectors in the Hilbert space. So here I've written this in a particular norm, which is the trace norm, and we want the moment over our state design ensemble to be epsilon close in trace distance to the Haar ensemble up to some moment k. And this trace distance, epsilon, is equivalent to the maximum bias of any measurement on k copies of the system. And in general, this is not trivial because the moments of the expectation are not the same as taking, the tensor copies of the expectation are not the same as taking the expectation of the tensor copies of the state. And I can give just some brief examples. So one example of a one design would be just a single qubit spin up or spin down with 1/2 probability of each. So this is an exact one design just for a single qubit system, but it's not a design for any higher order. We can also think about something like the Clifford group and single qubit stabilizer states. And these are 2 and 3 designs for a single qubit system, but not for k greater than or equal to 4. Okay, so now that we've covered states, let's try to generalize this to unitaries. So this requires us to be a little bit more careful because we have to specify what are the allowed measurement protocols when we think about how to distinguish a unitary ensemble from a hard random unitary. So the standard definition that's been most commonly studied is to allow for simultaneous measurements on k copies of the system. And this is equivalent to looking at the diamond norm distance between the two ensembles. So this is also what we call standard error or additive error designs, which have to reproduce the lower order moments up to k of any measurement on k copies of the system up to some small error epsilon. And here the diamond norm is essentially equivalent to the trace distance on some number of copies of the system, but also allowing for some arbitrary number of ancillas m to help us with our measurement. So again, this is a definition based on the maximum distinguishability of these two ensembles based on some measurement that we can perform on k copies of our unitary sample from the unknown ensemble versus the hard distribution. On the other hand, we're often interested in also analyzing computational hardness in settings that allow us to do adaptive processing and measurement steps. So in particular, we might care about this in the study of pseudorandom objects in cryptography settings. And there are a lot of classic examples of this, such as in quantum money, where you might want someone to not be able to distinguish two types of ensembles, or you might not want someone to be able to learn anything about your random objects, even if they're given many objects. So this kind of experiment is a little bit different because they could query your random unitary at several points in time and do some kind of processing in between. So these W0, W1, W2, all the way up to WK steps are some arbitrary unitary processing steps that they're doing in between each query. So they're allowed a maximum of k queries, let's say, and maybe they have a lot of ancillas as well. So this allows them to do a lot of things. Notably, it doesn't allow them to post-select on arbitrarily small possibilities of different measurements, but it still is strictly stronger than the other definition, which only allows them to use parallel measurements on the k copies. So this is also called adaptive security or indistinguishability under sequential measurements in this literature. So in our work, we introduce this new concept of measurable error designs to capture these outcomes of quantum experiments, which can use arbitrary processing steps, but use only up to k copies of the unitary that we sample. So we say that an ensemble is a measurable error design if in any experiment which uses these processing steps adaptively, the outcome of the experiment is still epsilon close in trace distance to the hard version of the experiment. And I won't show this in detail, but it is possible to show that this is strictly stronger than the other notion of error. On the other hand, because we haven't done any sort of post-selection on a very small measurement probabilities, this can still be efficiently measured in principle in a quantum experiment. So in some sense, we can think of this as the most physically stringent type of design error that's possible. Okay, and then we also showed that, in fact, one way we can think about this kind of adaptive security metric is to think about it in terms of a number of parallel, is to think about it in terms of parallel measurements on a number of queries, followed by a single post-selection at the end. And the way to see this is to look at this kind of tensor diagram picture where we pull out the copies of U onto the side, and then we can rewrite these lines here in terms of some disconnected qubits which are being fed forward into the experiment. And then at the very end, we just project these parts of our system onto NK bell pairs. And this is equivalent to doing the adaptive measurement or the sequential measurement using K copies of the unitary. So this turns out to be very helpful in simplifying the analysis for adaptive security. Okay, so now let me talk a little bit more about the construction that we introduced. So we present some new simple constructions that give us approximate state and unitary designs in depth log k times log nk over epsilon, and we show that the scaling is optimal up to leading order in all three parameters. So just for comparison, here's a table of some other constructions that were previously known for circuits that don't have all-to-all connectivity. So in particular, for the blocked random circuit, you'll see that the previously known best construction was log n, and for the structured constructions as well, the previous best known circuit depth was also order log n. So in our construction, we basically provide a way to compile a circuit in log n depth using some number of ancillas, which gives us this much better scaling. And just a caveat here that for technical reasons that I'll say a little bit more about, the scaling that's presented here is for a fixed epsilon, which is of order k squared over some parameter that's exponentially small in n. Okay, so let me talk about the state design first, just because it's a little bit simpler. So in the state design construction, we take blocks that look like these random phase states. So essentially, we start with something that is a plus state on every qubit. So equivalently, we could start in all zero state and then apply a layer of Hadamard to get all plus. And then we apply something that looks like a random phase operator. So essentially, this applies a random looking phase to every computational basis state, so plus or minus 1 to every computational basis state. And it turns out that we can actually do this in a sort of blocked out way, where we have different blocks where we apply random phases, and then we also apply another second layer of random phases on top, which overlaps with the first layer, or with two blocks in the first layer. And it turns out that this is enough to give us an approximate state design on the entire system. And as I mentioned before, it was known that the random phase state by itself will actually give you an approximate state k design up to k squared over 2 to the n. And it turns out that when we do this blocking procedure with blocks of size 2xc, so xc is the size of each of these wires here, so each of these blocks is acting on 2xc qubits. Then it turns out that we get an approximate state k design up to epsilon, which is order nk squared over 2 to c times c. And just a comment about how we do this in practice. So we can actually use a particular type of classical hash functions rather than uniformly random Boolean functions. And in particular, we can use these constructions of k-wise independent functions, which means that for this family of functions, if I take any k distinct inputs, then the output of these functions will also look uniformly random. And an example is that we can use polynomials over finite fields. So we can take the family f of x to be given by a sum of these a to the j times x to the j, where j runs from 0 to k minus 1. And each of these coefficients a sub j are also sampled from 0 to 2 to the n. And it turns out that when we replace the uniformly random functions or phases with their two k-wise independent counterparts, we get basically the same scalings. And so we can still get these approximate state k designs up to the same scaling, epsilon equals O of nk squared over 2 to the c times c. And the intuition for this comes from something very similar to this earlier work I mentioned from Schuster, Huang, and Hefferkamp, which uses this gluing argument to get the log n depth for random circuits, which have a more like uniform composition or uniform circuit construction. But here we actually do something a little bit different because we're gluing together designs with random phases instead. So here, each of these blocks on top is just a random phase operator. And this is enough to give us an approximate design on the whole system. And since we basically do this gluing n over c times or n over 2 to c times, then this will give us an approximate design on the entire system up to some error which adds, which each time we do it. So we get a total error that's n over c times whatever epsilon naught is, which in this case is exponentially small in c. And so the error is going to scale roughly as n epsilon naught over log n. Okay, and then it turns out that a very similar trick can be used in the unitary design case. So we can also get unitary designs up to measurable error epsilon using this. So here we start with the permutation phase Clifford ensemble. And here we have some arbitrary input state. And if we apply a random Clifford gate, a random phase gate, and also a random permutation, then whatever we get out will look like a hard random state. So we say that this ensemble is a unitary design. And in fact, it was shown that it's actually an approximate measurable error design for any k up to 2 to the n over 4 whenever these permutations, phases, and Cliffords are uniformly random. So one question is, how can we de-randomize this PFC ensemble to implement it in practice? You might guess that just like in the state design case, we can replace the random functions and permutations with efficient constructions of their two k-wise independent counterparts. However, when we do this, it turns out that the bottleneck is actually the permutation operators. They're more difficult to analyze and construct than our k-wise independent phases or our random Cliffords for technical reasons. And it has to do with the fact that we have to enforce this bijective mapping. But it turns out that we actually can get away without doing this. And we show this by introducing this Luby-Rakov construction on 2n bits, where we essentially shuffle some of the qubits based on their neighbors. So here, there's a left part and also a right part. So the left part shuffles the left half based on some function of the right half, and the right part shuffles the right half based on some function of the left half. And it turns out that if we do this, it's actually sufficient to replace the action of the random permutations. Okay, so we can essentially replace these permutations with a sequence of both the left and right half shuffling operators. And we can show that this object is also a measurable error design up to the same k. And then, as with the state design case, we can also do a blocking procedure where we implement these LFRC circuits on some number of blocks. And then we put overlapping phase operators, which each overlap with 2 of the blocks. And this is sufficient to also get us a unitary design up to some measurable error that we can bound. So in particular, we'll get the same scaling here, which is epsilon, which scales as O of nk squared over 2 to the c times c, where c is again the block size that we're applying each of the phase, shuffle, and Clifford operators to. Okay, and then just to run through again our circuit resources that we used. We need some number of circuit layers or circuit depth, which scales with each of these blocks that are used. So in the state design case, we just used 1 layer of Hadamard's plus 2 layers of these random phase gates. And then in the unitary design case, we have these 3 layers that require the random functions. And then we have 1 layer, which is a layer of random Cliffords. So the complexity of our construction depends just on the implementation of these 2 k-wise independent functions and the random Cliffords. And it's known that exact 2 designs, which actually are sufficient, can be implemented in depth O of log C with barely more than O of C ancillas. And then we also show that this Lagrange polynomial representation of the 2 k-wise independent functions can also be implemented reversibly in depth O of log k times log c with just more than kc ancillas. And if we don't want O of kc ancillas, then we can do it in slightly higher depth if we just have O of c ancillas, so O of n ancillas total. So we then get O of k times log c, which is now linear in k. Okay, so just to summarize again, we've taken these previous constructions and we've essentially reduced the scaling in n from log n to log n at the cost of some number of ancillas that scales with n times k. Okay, and it turns out that we can also get matching lower bounds for design depth using a counting argument. So in particular, for any k, which is sub-exponential in n, any circuit construction of a state or unitary design requires some minimum depth. So if we have a 1D circuit with up to O of n ancillas, this minimum depth is going to be at least k plus log n over epsilon. And with any connectivity and order n ancillas, it's going to be k plus log n over epsilon. And then finally, with no restrictions at all on the connectivity or number of ancillas, the scaling is going to be log k plus log n over epsilon. So essentially, we've saturated these last 2 bounds with our construction for k and for n and epsilon. Okay, so let me just briefly go over some of the ideas in our proof now. So to start, we want to ask, how can we think about the moments of the Haar distribution? So how do we actually compute the results of doing this twirling operation? So one thing that we can notice is that by definition, this is some integration over the unitary group, and it's symmetric under conjugation by any V tensor K, which is applied on either side, just by definition. So using some representation theory knowledge, we know that the only thing that this can look like is a sum of permutation operators. So here we're summing over some sigma and tau, which are permutations on Sk. And we have some linear combination of these permutation operators multiplied by something which is linear in X. But it turns out that there's an easier way to think about these moment operators by asking about the subspace that the moment operators live in. And we can see this by looking at the symmetric subspace, which is spanned by these particular basis elements, which are cat x, bra pi of x, for some bit strings x, where pi is any element of sk. Okay, and now how does this help us with our analysis of our designs? Well, the essential idea is that we can look at a proof strategy which looks at the moments locally and then tries to piece this together to bound the global moments and how close they are to a hard random state. And in particular, something that will help us a lot is to restrict to the distinct subspace, which is spanned by the basis elements where we only take x to be a distinct bit string. So this means that x1, x2, so on up to xk are all distinct. It turns out that we can show that most of the hard moments are contained in this distinct subspace. So in particular, if we look at the dimension of the symmetric subspace, this is just 2 to the n plus k minus 1 choose k. Whereas if we look at the dimension of the distinct subspace, which is 2 to the n choose k, then we can think about the fraction of the symmetric subspace, which is contained in this distinct subspace. And this is going to be 1 minus of k squared over 2 to the n. Okay. So this means that if we look at just the hard random state moments, which are again going to be equally distributed on the symmetric subspace, then we can also show that basically most of the moments are also contained on this distinct subspace. And so we can project onto this distinct subspace and still get something very close to the original hard moment up to some error, which is going to scale with k squared over 2 to the n. Okay, so now let's look at what happens when we combine two blocks and we do our blocking procedure. So we start with these two neighboring blocks where we have phase gates, and then we also have some overlapping phase gate on these two blocks. And because each of these two are themselves an approximate state design on this block of size 2c, we can say that this object is close to just doing a phase gate, which overlaps with two hard random states on each block. And using the trick that we discussed earlier, we can apply this restriction onto a locally distinct subspace on these two wires, or these two groups of qubits. And it turns out that when we do this and then we twirl over the random phase operator on top, this is just going to give us something which is uniform over the locally distinct subspace on the entire system. And it turns out that this is enough to give us something which looks uniform and very close to a hard random state. So now we do this n over 2c times. And this is going to give us an error which scales as n over c times k squared over 2c, because each phase block is going to give us a k squared over 2c error state design. Okay, and again, going to unitary designs is going to be very similar in the logic. And it turns out that the reason that the random Cliffords are helpful, or random 2 designs are helpful, is because they're going to allow us to use the same restriction to the distinct subspace strategy, because they allow us to basically bound the number of collisions in our different bit strings. So again, the proof strategy is going to be to compute the twirl over non-overlapping non-overlapping blocks of odd parity, and then we can glue them together with random phases on the even blocks. And one fact that turns out to be very helpful as well is that the projection onto the restricted subspace and the twirls over the different gates using random functions commute. And the reason this is because they're all acting in this computational basis. And so it's very easy to analyze all of these objects. So again, pictorially, what this looks like is that each of the blocks are going to look like something similar to a unitary design on that block. And then when we apply this random phase on top, this is going to be similar to doing a restriction or projection onto the locally distinct subspace first, and then applying the random phase. Oops. And then because of what we discussed earlier, again, this is going to be very similar to just applying a random unitary on the entire system. So similar to the state case, we can think of these random phases as essentially gluing together locally distinct subspaces. And we can also take this one step further. Because of the fact that we're just relying on the idea that our locally distinct subspaces glue together, we can actually modify our circuit architecture a bit. So for one, we know that all of these objects, when we're twirling over the random functions, they can actually be moved around past each other. So we can move our L, R, and Fs around. And we can go even further. So in particular, we actually don't even need each block to be a full unitary design. We can actually just have L's and F's here. And then as long as we have some shuffling operator in between each block and the random phases between each block, this is also sufficient. And then we can also just apply random Cliffords to one of the incoming blocks, which is used to shuffle its neighboring part of the block. And this construction on the right is actually the first one that we present in the paper. So as you could see, it's a very simple construction. Okay, and then I just want to comment a little bit on how this differs from the original gluing lemma that we discussed. So in the original gluing lemma, each of these blocks are actually unitary designs, whereas in our construction, we actually don't need that these blocks on top form unitary designs. We also don't need these blocks here to be unitary designs because we just need the property that after twirling over each block, the locally distinct subspaces glue together and cover enough of the global distinct subspace. However, it is possible to also naively apply the techniques from this previous paper to an ensemble where we do have the L, R, F, and C gates in each block. And this actually gives us something that is kind of close to our result. So we get an epsilon scales as order nk squared over 2c. So this is not quite the same. And also requires several more layers of gates in comparison to the ensemble on the last page. I also want to mention that our techniques can also be used to analyze pseudorandom states and unitaries. So by pseudorandom, here I mean that these are ensembles which cannot be efficiently distinguished from hard random ensembles in any experiment with poly-n resources. So this means that we can set k to be poly-n, and we still want an epsilon that is small in n. And it turns out that if we just replace our two ky independent functions in our construction with the classical pseudorandom functions, then we get pseudorandom quantum states and pseudorandom unitary ensembles. And using our techniques, it's also possible to prove that these ensembles are pseudorandom in a much simpler way compared to previous proofs. Okay, so let me just leave off then with some conclusions. So just some takeaways. Highly structured circuits with very mild long-range connectivity, which is only on the order of log n, can actually form designs in exponentially lower depth than uniform 1D random circuits. And although we don't say very much in our paper about practical implementations, these structured constructions and some of our techniques for analyzing them are likely to be useful in practice because they allow you to play around with trading off between different circuit resources. And there's this follow-up work from another group which analyzes some of these trade-offs. And in fact, they show that if you inject the classical degrees of freedom in a certain way, it's actually possible to get designs in constant time. Okay, and then in terms of open questions, I do want to highlight that although I said that we achieve designs in nearly optimal depth and its leading order optimal in nk and epsilon, we don't actually achieve this additive scaling, which is log k plus log log n. Our scaling is actually log k times log log n, k over epsilon. And so it's an open question as to whether it's possible to achieve the additive scaling. And then, as I said earlier, more detailed analysis is also needed in discussing the trade-off between circuit resources required for practical implementations on near-term platforms. Finally, I also want to highlight that there are some broader open questions related to beyond hard random unitary ensembles in quantum dynamics. So for example, you might often care about more structured ensembles or things that have conserved charges and physical dynamics and so on. And so this work didn't really touch on any of that, but we hope that our techniques can be helpful in understanding some ensembles that are also useful for more practical purposes other than just random unitaries. Okay, so that's all I have prepared for today. Thank you again for having me, and I'm happy to take any questions.
All right. So thank you very much for a very splendid talk with some very nice results. Yeah, so we can now open the floor for questions. So if you have any questions, comments, please feel free to just unmute yourself and ask it now. Let me see. Anyone? Okay, I don't see anyone yet. So maybe I can go first. Yeah, so when you have these constructions, I always notice that it always uses this kind of brickwork, right? So, but my intuition is kind of like what you really need is you just need to have kind of enough mixing in the circuit to kind of get the randomness that you want. So, like for example, is the kind of the brickwork just following from like the proof technique? I imagine, for example, that maybe I can have the number of like blocks that you needed by having something in a pyramid, like having just triangular things. So it's not quite the full brickwork, right? Like so you only have like one thing and then two and so on. That this kind of structure. Maybe you can even remove more blocks somewhere else if you kind of have enough mixing in the other places. Yeah, I don't know. Like maybe this is kind of a stupid question, but maybe you
No,
have
that's
some comments.
reasonable to ask. Yeah, so it's true to some extent that you just need the circuit to be well enough connected in order to get mixing. So yeah, there is an alternative way of analyzing this in terms of like the number of gates you need and the kind of connectivity you need. And it's true that as long as the circuit is sort of sufficiently uniformly connected in some sense, you can still show that it'll eventually form an approximate design. It just turns out that the brickwork way of thinking about it, where we have like nearest neighbor overlapping blocks in every layer, happens to be very nice to analyze, right? Because I guess also from a practical perspective, if you really want to prepare a random looking circuit very quickly and you want to prepare as many states and unitaries as possible very quickly, then you would probably want to have more gates if possible.
Okay. Just general comment. So do you try to optimize your ancilla cost? Because it seems to me that if you have this, if your ancilla cost is proportional to n and also k, there seems to be a lot of rooms for you to further improve, right?
Oh, that's a good question. So actually our ancilla cost is also close to optimal.
Okay.
Maybe I can go back to this page. Right, so there is a particular reason why we can't do better, and it has to do with this county argument detail. So the reason is that we effectively always need a certain number of degrees of freedom to repair a K design. This number of degree of freedom is going to scale as 2 to the nk. And so when I have a very low depth circuit like this, I do need a large number of ancillas just to have enough degrees of freedom in order to form a design. So in fact, you need on the order of nk total gates. So whether that's coming from ancillas or gates just in your primary system.
I see. So this nk, is this more or less the space and time overhead that you need to have? Like this is the lower bound?
That's right. It's a tight lower bound. Yeah.
I see. Okay, good. Thank you.
All right. Let me see. Do we have any more questions? We have a bit more time. So okay, maybe I can ask another one. So I've sort of like studied some of the earlier work related to pseudorandom unitaries, especially the PFC ensemble. So I was just curious, like, I mean, like for okay, for the construction, at least for the part that I understand, so you're still kind of so the phase part you're kind of replacing with k wise independent function, and the permutation is being replaced by some construction that's sort of like indistinguishable from permutations with this Lubirachov, this kind of Feistel kind of construction. But I'm just wondering, like, because like what actually does it, what properties of the PFC does it really make it kind of like approximate the unitary design? I always kind of like imagine that how much of the permutation structure do you really need in order to kind of like, for example, still get an approximate unitary design? I always kind of fantasize that you don't really need kind of like a permutation there. But I suppose, but my understanding also is that part of it, if you really go through the proof, is kind of getting things to work in the distinct subspace. Yeah, so I don't know. I mean, okay, maybe I didn't really ask any question there, but I just wanted to get your kind of comments or opinion on this.
Oh, that's an interesting thought. Yeah, it's true to some extent that really what the permutation is doing is kind of like shuffling things around and trying to cover this distinct subspace uniformly, as you said, because our input could be very non-uniform, but we want to shuffle it around so that kind of uniformly covering the moments. Yeah, I'm not sure in terms of like what further optimizations there could be done if that's the question. I think there is this other work that just came out from some of my collaborators, Tommy Schuster, Robert Huang, and so on, where they are primarily looking at a stronger definition of unitary designs. It's primarily a paper about strong unitary designs, but they also discussed a modification of this kind of Luby-Rakoff construction, where instead of using extra ancillas, you can instead use some more neighboring qubits instead. So there might be some further optimizations in that direction. And so that is like sort of one other potential way to think about it is like, are there other applications of this kind of idea of like shuffling by conditioning on your neighbors instead? And is that sufficient to get something that looks very random as if you did like random shuffling that's like uniformly random in some sense?
Okay, I see. This work is available already on the archive, or?
Yes, that's right.
Okay, then maybe I
go back.
check it out later.
Yeah, both this work and also this follow-up that I mentioned from Tommy Schuster and Robert Huang are available on the archive. And yeah, the follow-up work is primarily on strong unitary designs, but they do also talk about ancilla-free constructions. Right. Although I want to mention a caveat is that in their work, because they're primarily looking at strong unitary designs, they only look at constructions that have log n depth scaling, because it turns out that is the lower bound for that setting.
Okay.